Can you hear me, Piotr?
Yes.
Okay, excellent. Okay. So, welcome back, everyone. Today we'll have our first keynote speaker. He's connecting remotely from Google in London, I guess. So Piotr has been a research scientist at Google DeepMind for almost 11 years. So he joined shortly after the acquisition of DeepMind by Google. Prior to that, he worked at Microsoft, Bell Labs, and he completed his PhD at New York University under the supervision of Jan LeCun, which is now the director of AI research at Meta or Facebook, and awardee of the Turing Award, which is the most renowned prize for computer science. So Piotr today is going to tell us about some of his research on using neural networks to either model the weather, so the atmospheric of the planet, or using these sort of models to also forecast ahead. So please welcome our speaker, and Piotr, you have the stage.
Fantastic. Thank you so much, Hugo. I'm really delighted. I'm honored for the invitation. I'm sorry not to be with you in person, but I'm going to be available to follow up by email. I'm going to leave my email at the end of the talk so that you can write to me and ask me lots of questions. So, neural weather forecasting and neural compression of atmospheric states. This is the very dry title of this presentation, which will be a little bit like a journey and an overview of research that we have been conducting in our team, as well as the various problems we've been facing. But I first need to start with a disclaimer. So, this talk is not about the following types of aspects. It's not about actual numerical weather forecasting, numerical weather prediction, NWPs. I have great admiration for the physicists and mathematicians who are able to model the atmosphere, including before the very first computer was built. And I'm thinking of Lewis Fry Richardson, who in the 1920s derived manually a 6-hour forecast. Well, it took him 6 weeks to manually do it. So obviously computers did help, but he already theorized a lot of the principles behind it. So traditional numerical weather prediction starts with physical principles, the conservation of mass, conservation of energy and momentum, to derive equations for a load of processes happening in the atmosphere and the oceans. These are described by partial differential equations, PDEs, that generalize well, and a good example of them is the Navier-Stokes equations. These are the governing equations of the Earth weather. However, they do not have a known closed-form solution. So NWP-based forecasting models require to be solved numerically, approximated. And those equations are typically solved on a discretized grid. Commonly used methods include explicit solvers and steps. And basically they step through a current atmospheric state forward in time based on local information. And that slide contains one equation I cannot understand myself, which is the heat equation developed by Joseph Fourier to model how heat diffuses in time through a given region. But as I said, in this talk, we are not going to use physics-based equations. We are not going to even use physics-based neural networks. We're just going to use traditional deep learning, so to speak. And what this talk really is about is metrics. How to evaluate if those methods work and how and when they fail. Lots of metrics. So as an anecdote, Hugo and I met and became friends back on my first day at Microsoft Bing in 2013, when the two of us were working on the second most popular search engine, Bing. And so every day we would stare at pages and pages of metrics that evaluated the quality of the models that we were building and all the edge cases, all the failure modes. And we needed to make sure that the product, query auto-suggestion, was not failing in any of those metrics, in any of those edge cases. All right, weather nowcasting, weather forecasting, and climate outlooks. These are the three domains I'm going to cover in this talk, and they range effectively at different spatial scales, from the local scale at the country level now up to the global scale, and different time scales from a few minutes, a few hours, up to years and decades. The first problem is nowcasting. Nowcasting has the shortest lead time, and it's literally forecasting in a very short span of, let's say, 2 hours. That's the work that we started, and we built upon that expertise towards larger timescales and larger spatial scales. In nowcasting, the predictability of the weather comes from short-term, high-resolution observations. In weather forecasting, and I'm going to mention a bit the work of my colleagues working on GraphCast, predictability comes from initial atmospheric conditions. And finally, when working on time projections, predictability comes from sea surface temperature conditions. Let's start with the simplest model, the simplest case, precipitation nowcasting, which was the subject of a paper we published in Nature back in 2021, and here is the whole list of authors and the title, Skillful Precipitation Nowcasting Using Deep Generative Models of Radar. And I think the most important word in this is generative. So back in 2017, late 2017, when we thought about working on this problem, Google DeepMind was mostly a theoretical research lab focused on games and simulation and on reinforcement learning. Some people, like me, were interested in applications of AI to the real world. And for this project, weather forecasting, we needed a partner, an additional expertise. So we joined our forces with the British Meteorological Office, the Met Office, which was founded 150 years ago, and which has pioneered the science of meteorology. So I have a little anecdote. The D-Day was moved from the 5th of June 1944 to the 6th of June 1944 because of unfavorable weather conditions which were predicted by the Met Office. So this is a first probably application, a real-world application of very strategic importance of weather forecasting. What I loved most when we worked with the Met Office was that we controlled our approaches. So I mentioned already numerical weather prediction models, which were used by the Met Office, and our machine learning approaches. And we found that precipitation nowcasting was standing out as a perfect opportunity to apply machine learning techniques. So in this very first part, the talk, I have even 5 smaller parts. And let's start with the first one, the statement of a problem, what this was about. Precipitation nowcasting is the high-resolution forecasting of rainfall up to 2 hours into the future. It is crucial for weather-dependent decision-making. Nowcasting informs the operations of a wide variety of sectors, including flood early warning systems, air traffic control and marine services, emergency services, energy management, etc. And we believe that the nowcasting problem is interesting from a data science perspective for 3 distinct reasons. First of all, nowcasting needs to be useful and provide accurate predictions across multiple spatial and temporal scales. Second, nowcasting needs to account for the uncertainty and be verified probabilistically. And third, it needs to perform well on heavy precipitation events that are rare, but that do critically affect human life and economy. And our work here focused on the UK. The nowcasting models were trained and evaluated on data from a collection of Doppler radars from the Met Office network, which is about 15, 16 operational radars covering 99% of the UK, and which at the end produce images of 1500 by 1200 pixels, where each pixel, each grid cell of a composite image represents the surface level precipitation rate over a 1 kilometer by 1 kilometer region. And this is expressed in millimeters per hour, how much rain falls in 1 hour. Thanks to the Met Office data provisioning team, we were given radar composite images every 5 minutes since early 2016 and up to 2019. And that represented several terabytes of data. So we were already in a big data regime. And as we started working, we needed to check the baselines. The very first baseline, obviously, was the one already in use by the Met Office, called STEPS, and its corresponding open source Python library, PySteps. And these were industry standard models for probabilistic precipitation nowcasting, which relied on multi-scale optical flow. So optical flow was estimated from recent radar images, consecutive radar images, with some additional smoothness penalty. And that was used to define a 2D motion field called advection field. And using that advection field, STEPS would extrapolate, using semi-Lagrangian extrapolation, the most recent radar images in order to make predictions. And because of the application of stochastic perturbations in rainfall intensity and stochastic perturbations of the motion field, the team working on STEPS could actually obtain different realizations for ensemble nowcasts, from which they could derive probabilistic and deterministic forecasts at multiple spatial scales. So even if the system was deterministic, the random noise was providing, the random initial conditions were providing variability, and they were useful to estimate likelihood of rain. Early narrow research, we therefore tried to improve upon optical flow-based methods, and we tried to learn them using a differential approach. We used state-of-the-art PWC nets, pyramidal warped cost volume networks, which at that time was the state-of-the-art for estimating optical flow from sequences of consecutive images without labels. The problem was the boundary of the images, where information was missing. The neural network would basically learn creative ways to make up predictions, basically smudging the rest of the image. And that was not physically plausible. So we ended up not using PWC nets. We tried various deep learning baselines, most of them based on units, the sort of architecture that has compression and decompression, or encoding and decoding step. And the strongest state-of-the-art baseline was coming actually from a team at Google. At that time, DeepMind and Google Research were separated, and there was this team led by Nan Kajbhana, a former DeepMinder, working on MetsNet. And so their approach was a convolutional recurrent network, a convolutional long short-term memory encoder, and an actual attention decoder. So a form of transformer architecture for the decoding. And what we did was to take their approach and adapt it to our setting, and I was responsible for that. I tried to really make it work as well as possible to have a strong computing baseline. And we managed to get very good performance in terms of metrics. And I will go back to those metrics. But there was one problem. The predictions were blurry. All right, so we needed something different. And this is where the word generative comes into play. Our approach and our desiderata was to have a model that is consistent across spatial and temporal scales, that captures rare events, and that properly accounts for uncertainty. So what we wanted effectively was to have some sort of neural sampler which generates multiple realizations for a given prediction, just like numerical prediction models do, and just like STEPS and PySteps do, thanks to random initial conditions. And thanks to that multiple realizations, we would be able to calculate the uncertainty of predictions in order to give a probabilistic forecast. So this is why we settled for conditional generative adversarial networks. Basically, your standard CGAN from the late 2010s. We built upon the work of our colleagues from DeepMind, who have published previously BigGAN, as well as DVGAN for video prediction. So generative models, as you know, are a very popular class of algorithms that learn to approximate the distribution of observed data X and to generate samples XS from that distribution. They are built using a deterministic model, like a neural network, that incorporates stochasticity through latent random vectors Z. When fed with a random vector Z sampled from multivariate Gaussian, those models can generate samples from the learned distribution. Conditional generative models predict a realization XS, conditional both on the latent random vector Z and on a conditioning variable Y, which could be the past radar estimates of surface precipitation. And the target variable XS would be the future instance of radar fields. And a specific type of generative models, called generative adversarial networks, relies on adversarial training to train both the generator and a discriminator between the output XS coming from the generator, fake output, and the real target XR from the dataset. Our architecture was the following. We would take 4 consecutive radar observations of precipitation, so millimeters per hour at a 1 kilometer resolution, from the previous 20 minutes, so every 5 minutes. And we would feed that as context for the generator that would then sample multiple realizations of future precipitation, each realization being 18 frames long and covering 90 minutes. During training, the generator would take inputs that are 256 by 256 pixel images and output similarly 256 by 256 frames. And learning would be driven by 2 loss functions and 1 regularization term. The first loss was defined to be a temporal discriminator, a 3-dimensional coordinate that would distinguish observed and generated radar sequences and impose a temporal consistency to basically penalize jumpy predictions. The second loss was a spatial discriminator, again a convolutional neural network that distinguishes individual observed radar fields from generated fields, and that ensures spatial consistency and that discourages blurry predictions. We wanted to avoid the blurriness of existing deep learning models. And finally, we needed to also have an accurate model, not just something that makes up images of brain, but actually that makes images that follow the context of previous images. So we need to introduce a regularization term, which penalized deviation between the real radar sequences and the mean of the predictions given by the model. And that first term was important to provide location-accurate predictions and to improve performance. So digging a little bit into the generator had a conditioning stack processing 4 radar images that I mentioned earlier, the context, and that stack structure allowed information from the context to be used at multiple resolutions, down to an 8 by 8 map. And it will produce a context presentation that will be used as an input to the sampler. Then the sampler was a recurrent neural network made of convolutional gate and recurrent units that use the context and the later representations as inputs. The sampler would make predictions of 18 future radar fields over 90 minutes, and the output of that conditioning stack could be seen as the initial condition for the sampler. That sampler still needed a source of stochasticity, the random perturbations, which came from the latent conditioning stack, taking samples from a Gaussian distribution covering a spatial 8 by 8 map, and which was reshaped into different layers. And that noise would be added at every step to the convolutional GRUs of the sampler. So essentially, these additional latent variables accounted for uncertainty. All right, so that's the architecture. We trained it and we validated on random samples of crops from the radar, 256 by 256 images, cropped across the UK. And during training, of course, we needed to use important sampling to account for the fact that it doesn't rain actually that much in the UK, unlike what they keep saying. So we created a data set that is more representative of heavy precipitation and to capture rare events. We evaluated that model on a test set from 2019, the year on which we didn't train. And our model was fully convolutional, which meant we could apply it out of the box onto a much larger radar image that would cover the entire UK. Even if we train on small crops, we could apply it on a giant image. The radar conditioning and the latent variables were convolutional, and that allowed us to train on small crops while having spatially temporal consistent predictions on larger frames. Once trained, this model allowed full resolution nowcasts to be produced. And at that time, on an NVIDIA V100 GPU, it would take about 1 second per frame or half a minute on CPU. So that was the huge differentiating aspect compared to numerical weather prediction methods or even to the optical flow baseline pi steps. But the crux of our paper was the evaluation and the metrics that we used to compare the models, because we wanted to understand where our generative model would outperform the other models, the other baselines. The first metric was the critical success index, CSI, which measures the location accuracy of a forecast at various rain rates, 1 for 8 millimeters per hour in this case, on this plot. And that CSI was a ratio of true positives over true positives, false positives, and false negatives in the denominator. And all the deep learning systems would produce forecasts that were significantly more location accurate than the baseline from the Met Office steps. However, there was not much difference between the deep learning models using the CSI metric. So, interestingly, that CSI metric didn't account for blurring predictions and the various ways that the models could cheat, essentially, to score better. We needed new metrics. We looked at other interesting metrics, like the power spectral density, PSD, the Fourier transform of the image data, plotted where the power is plotted versus wavelength. And those PSD plots would show that both the generative model and pi steps match the observations, the black dotted line, much better than the other deep learning models. They match essentially the spectral characteristics, and they didn't lose the important spatial high frequency content. The PSD plots also show the predictions from the MetNet actual attention-based model baseline had much less small-scale variability. So they were more smooth, more blurry, and they would get worse when we increase the prediction horizon, which of course reduces the value of those nowcasts for meteorologists. So here, this figure illustrates the ensemble variability of the GAN, of our generative model, for 6 different realizations. And so 6 different columns correspond to 6 different realizations, and 3 different rows correspond to 3 different time steps, t plus 30 minutes, t plus 1 hour, t plus 90 minutes. And you can see that the differences across realizations are rather small, but they still have the same spectral properties, frequential properties as the original. These realizations differed less from one sample to another from the realizations from the ensemble model from the Met Office. So now we needed to compare the probabilistic metrics between the models. And for probabilistic verification, we used the so-called continuously ranked probability score, CRPS, which is basically the difference between the mean error and the intersample mean variability. So it's almost like a mean variance trade-off. This is for different realizations. So we compute that those statistics on the various realizations of precipitation rate and also on the average precipitation rate, and we aggregate then over regions of increasing size. And when measured at the grid resolution level, the generative model, pi steps, and actual attention would perform similarly. But as the spatial aggregation would increase, the generative model and pi steps from the Met Office would provide strong, consistently strong performance, the best one being the generative model, whereas the deep learning actual attention model was significantly poorer on larger aggregations and would outperform those methods. And then we looked into single case studies, specifically trying to understand what sort of errors were produced. And so here we looked at, for instance, a case chosen by the chief forecaster at the Met Office, who selected some rain over Scotland. And so in his terms, this corresponded to convective cells coming from the evaporation, forming spotty clouds and giving intense showers over land. And we noticed that our method, generative model, was actually performing relatively well compared to PySteps, and was much more fine and precise than the non-generative model actual attention. Traditional models like PySteps, what they do is that they apply optical flow, but they often overestimate rainfall intensity over time. Something which is not observed in reality and doesn't sufficiently cover the spatial extent of rainfall. And whereas actual attention model, deep learning baselines, roughly predicted the location of rain, but because of aggressive blurring, they would overpredict areas of rain, and sometimes they miss the actual value of the intensity, and especially they would fail to capture small-scale structure, which is very important for meteorologists to understand what sort of rain is coming. By comparison, our generative model preserved those spatial structures, represented convection events well, and maintained heavy rainfall in early prediction. So unsurprisingly, when we showed this nowcast to expert forecasters, they definitely preferred the predictions made by the generative model. And this example, this case study highlighted the limitations of using existing metrics to evaluate forecasts. Those metrics implicitly assumed that the models made sense, like numerical reprediction models and advection-based steps preserve the physical plausibility of forecasts, whereas deep learning-based methods, they just trying to fit the data, no matter how. And sometimes they are more flexible, but they try to gain the metrics, and even if they seem to outperform other systems, they fail to produce useful predictions. So we need to be a bit thoughtful about the application of deep learning to make sure that the metrics discriminate between different approaches well, and we needed to ask the expert meteorologists who have that knowledge for their opinion. This is what we did. We designed a new study, a new type of evaluation based on expert judgments who assess the performance of nowcasting methods. We worked with 56 meteorologists for the Met Office and with the chief forecaster, who did not participate in the study, to design together a study and the type of assessments. And the hope was that that study and expert verification provide us with insight into the usefulness of machine learning in an operational setting to inform better decisions on developing machine learning methods for nowcasting. The experimental protocol was the following. First, we would show the different realizations of nowcasting to the expert participants. So, and it relied on preference ranking of predictions coming from three sources: the ground truth, the optical flow-based method used by the Met Office, and the deep learning baseline, the actual attention, and our generative model. The ground truth will be on the top row, and then the bottom three rows would be those three methods, but in a random order. And then the participants would be shown cases of a high precipitation data selected by the chief meteorologists, and they would need to basically look at that and check which one of the three candidates proposed by the computational methods actually matched the best the ground truth predictions. Then the participants were asked in a form to rank the model predictions compared to the ground truth, and also to leave comments. So the sample of participants were selected at random. A sample of those participants was selected at random to complete a second phase, a retrospective recall interview, where they asked to review the rankings from phase one and to explain their decision. And during that interview, researchers tried to build a picture of a cognitive process for decision-making. And important features were recall of a task, details of emotive reasoning behind decision-making, blanks, mistakes. And the researcher would take notes to understand the explanation from the participant experts. And here the results were drastic. Because most forecasters selected the generative model as the most preferred method, the second most selected was the steps model from the Met Office, and only in the third position, the other deep learning method. And the key factors included the ability to capture well the extent of a rain, even when intensity wasn't quite right. And that result contrasted with the quantitative verification scores that don't necessarily give enough indication of a difference between competing approaches, and that often tend to favor models that blur forecasts over time. We're very happy about running this operational assessment, and we think that this sort of experimental psychology studies in atmospheric sciences could actually give us additional insight into meteorological decision mechanisms. But most importantly, this is useful for ensuring that machine learning-based products can deliver value in an operational context. So kind of the guiding principle here is to keep the human in the loop. We want to provide decision-making value for real-world experts, and we build deep learning models that are actually preferred by professional forecasters rather than simply match a selected set of metrics. Okay, so this was the work on nowcasting. And now let me look into different scales, different spatial scales and different temporal scales. And I'm going to say a few words first on GraphCast, the work of my colleagues who work on medium-term weather forecasting up to 14 days ahead. So medium-range weather forecasting is generated by simulations run on large high-performance computing clusters. It involves two main components. The first component is data assimilation, the process of inferring and tracking the weather state based on recent and past observations from satellites or weather stations. The resulting output of data assimilation is an estimate of the most recent sequence of weather states. The second component is a forecast model to predict the evolution of the weather state. Traditionally, data assimilation and forecasting use the numeric weather prediction model. Previous forecasts are used to inform data assimilation, and most recent analysis is used as an input to the forecast model. And NWP methods scale well with compute. Accuracy increases if you increase the amount of computational resources and if you have high-resolution simulators. And actually, some of the largest supercomputers in the world are used to make forecasts for the weather, like the Met Office. But NWPs, numeric weather prediction models, do not scale well with increasing amounts of available data. They're improved because highly trained experts manually innovate and develop better models, algorithms, and approximations. Then there is the term reanalysis, which I need to explain. This is performing data assimilation on historical weather observations in order to estimate the full state of the weather globally over time. An example of reanalysis data is ERA5. It's the most comprehensive and accurate reanalysis archive in the world, and that reanalysis data is essentially a best guess reconstruction of past weather using simulated and observed data. And the kind of data this contains is temperature and wind speed, east-west and north-south, and humidity at multiple levels in the atmosphere. And we don't actually talk about height, but rather we talk about pressure levels, isobars. And so we don't actually express the pressure at different levels, but rather we take a level, let's say at 500 hectopascals, and we express the geopotential, which is the height of a column of air to get at 500 hectopascals. And then there are also surface variables, such as wind speed at 10 meters, or temperature at 2 meters, or precipitation on ground level, or sea level humidity. The most accurate medium-range weather operational forecasting system in the world is based on NWPs. It's called the Integrated Forecasting System. It is hosted by ECMWF, the European Center for Medium-Range Weather Forecasting, and it's comprised of two components. HRES, which is a deterministic model that produces a single 10-day forecast at 0.1 degrees latitude longitude several times a day. And ENS, an ensemble model that produces 50 stochastically perturbed forecasts over 15 days at a slightly coarser resolution of 0.2 degrees of resolution, again, several times a day. And stochastic perturbations means changing the initial conditions and propagating the perturbed state through the deterministic system. The team behind GraphCast started working in 2022 on the problem of learning medium-range weather forecasting on ECMWF data provided by ECMWF, this reanalysis data called ERA5. This slide shows examples of temperature and wind and at temperature at 500 hectopascals and on the surface. And they built upon existing work, the most notable of which was a single author paper by Keisler, published in early 22, that introduced a graph neural network-based model and which reported results on a 1 degree latitude-longitude resolution and a 6-day forecast, which already started approaching the skill, predictive skill of HRES on several variables and pressure levels. Other papers they considered, including work by NVIDIA researchers on Fourier neural operators and vision transformers, or Pangu Weather in China based on vision transformers. And the specificity of the work done by the GraphCast team was to use encoder, processing, and decoder architecture and graph neural networks. So effectively, the graph neural network system would produce autoregressive prediction of the forecast trajectories. The encoder map would convert 2 consecutive frames of latitude-longitude input grids, so these rectangular images, into an icosahedral grid with hundreds of variables per grid point and multi-scale, an internal mesh representation that was multi-scale. Then the processor would perform many rounds of message passing on this multi-mesh, multi-scale mesh. And what was interesting with multi-scale mesh is that it had different sorts of connections. At local connections, or locally, spatially close, and long-range connections. And that enabled to have efficient communication, message passing, without requiring an explicit hierarchy. And finally, there was this decoder who would map the multi-mesh presentation back to a latitude-longitude grid to use as prediction for the next time step. And in order to quantify the skillfulness of GraphCast and other machine learning models and HRES, the baseline, the team at the time focused on deterministic forecasting. So they only used one metric, which was the root mean square error, computed against ground truth data. So root mean square error would measure the magnitude of the differences between forecasts and ground truth. And on this on the slide, you can see results for 2 variables, the mean sea level pressure in hectopascals and east-west component of wind at 10 meters. And you can see sequences of states from ERA5, the HRES forecast from ECMWF, and GraphCast. And at 3 different horizons, 2 days, 6 days, 10 days. And then you see 2 rows. The 4th row is the absolute difference between HRES forecast, ground truth, the ground truth at that time, and the HRES forecast. And the 5th row is the difference between the ERA5 ground truth and GraphCast forecast. And finally, the last plot, the bottom plot, is a line that shows the root mean square error growing in time, because errors accumulate over time, between the forecast and the respective ground truth, comparing HRES and GraphCast. And you can see that actually GraphCast is overperforming the baseline of HRES, so the method used in deployed. So already by 2022, 2023, they had a state-of-the-art model, but it was outperforming the state-of-the-art. And their work has been prominently recognized. First of all, it has been adopted by ECMWF and by many researchers around the world. You can actually see the results on the ECMWF website itself. The team has been recognized by the medal of the Royal Academy of Engineering, and you can see here the team led by Remy Lam. And the work has been useful to actually predict hurricane trajectories better than existing models. All right, so that was weather forecasting at the short time scale, nowcasting. We're forecasting at the scale that we are typically using up to 2 weeks. And now we're going to look at longer range climate data. Or rather, maybe I'm hyping expectations a bit too much, on one specific subset of a problem that needs to be addressed first, which is how to represent and compress that huge amount of data. So this is the work about climate data compression. Neural compression for atmospheric state is the title of our paper that we put on arXiv as a preprint. And the team who has been working with this includes Suman Ravouri, who started the project, and then I took over from him. David Ward-Farley, who has been leading the infrastructure work, and then Yana Hasson, Shakir Mohamed, Matthew Grimes, Simon Osindero, Hyunjin Kim, Melanie Ray, and Mihaela Roska. So let's start with the statement of a problem. A substantial portion of weather and climate simulation outputs are the atmospheric states, which are derived from reanalysis, which I mentioned earlier. So running a weather model and matching it to the actual observations. And there are many stakeholders, researchers, policymakers, insurers, who use this data to better understand the Earth system and to guide policy decisions. Our colleagues from the weather team use these machine learning approaches for weather prediction. The problem is that all those dense time series of high-dimensional states of the atmosphere comprise an enormous amount of data. We've seen that there are many variables, and we talked about pressure, wind speed, humidity, precipitation, temperature, not only on surface, but also at 13, 25, 37 atmospheric levels of pressure every hour, every day for 100 years. And as climate models gain in spatial and temporal resolution, they demand considerably more space. Translating those numbers into required data storage would lead to a 15,000 times more data in order to have storm resolving models, and 15 million times more data for cloud resolving models with a meter scale resolution. So we simply need to compress that data in order to make the problem tractable and not to have to discard data. And data storage is a problem. And this is the motivation for our first work on compressing climate data. Apparently, according to a recent paper from 22, climate research generates 260 terabytes of data every 16 seconds. ERA 5 by itself is a quarter petabyte. CMIP6, which is a climate data set, is 0.1 to 1 petabyte per trajectory. And it's expected to increase. If you wanted to store hundreds of such trajectories, the cost, let's say on Google Cloud or Amazon Cloud or Azure Cloud, will be of the order of millions of dollars per month. This forces research labs to literally discard valuable data. There are many interesting scientific challenges also coming with compression. How to do lossy compression right, how to handle spherical representations, and how to handle rare and extreme events. And our objective here was to achieve a strong compression ratio of a factor of 100 or even 1,000 while preserving data integrity in order to facilitate data sharing and to accelerate climate research. And our baseline was a model published at EPFL by Huang and Höfler that essentially was overfitting the data set, but was learning a functional representation going from spatial and temporal coordinates to atmospheric values. But what they noted is that at a compression ratio of, let's say, 1000x, rare events would be erased. And that, like this hurricane, for instance, here, and that would be problematic. So we needed to address this problem, and the step one of our problem was to actually understand how to represent data on a sphere without using spheres. And we did that because we didn't want to use graph networks. We wanted to use convolutional networks and essentially spatial grids, rectangular grids. So we conducted an extensive evaluation of different projection methods. One of them was the yin-yang grid. So you take a sphere, and then you create one rectangle that wraps around the equator, and a second rectangle that goes from the north to the south pole. And these two grids are slightly overlapping, obviously. A second method is called cubed sphere. You take a sphere, and then you create 6 faces on that sphere, and the lines correspond to the great circle lines. And the third projection is called Hupix, and this one is actually adopted the most by the community. The reason for this is that it's a projection that cuts a sphere into 12 diamonds, 4 joining at the poles, North Pole, 4 joining at the South Pole, and 4 on the equator. It slightly distorts the shape, the angles, but it preserves the areas. So if you take a pixel in any of one of those squares, it has essentially the same area. So it's useful for preservation of mass, for instance. And our approach was the following. So our neural data compression system would take the global surface and atmospheric data from multiple variables, different channels and different pressure levels, and we would project it on 12 Hupix squares. This plot shows 3 such squares, the green, red, and blue one. And so that data would be correspond to a single atmospheric state at a given time step. And those separate channels would be compressed separately to create 256 by 256 squares of quantized representation, like that. So actually, sorry, a single Hupix square containing multiple channels will be compressed into a single representation. And during training and evaluation, we would reconstruct from that compressed code the Hupix square. So starting from the quantized representation, we would decompress the Hupix square. So now we introduce error, decompression error. And after reconstruction, we would compute spherical harmonics coefficients on those Hupix reconstructions. And those spherical harmonics coefficients would be used to synthesize reprojected images on the latitude-longitude coordinates. So essentially, we use spherical harmonics as a way to do projection back onto latitude-longitude, but also to derive spectral properties on the signal. And the metrics that we computed during that reconstruction included just comparing the reconstruction versus the ground truth in Hupix space, in Hupix projection, but also, because we use spherical harmonics, the power spectrum of a reconstruction. And finally, we would compare the reprojected reconstruction in latitude-longitude space between the ground truth and the reconstruction. This image here shows one of the problems that arises when using representations of a sphere into small chunks. It's the appearance of stitching artifacts. And this is something that we noticed when we were looking at the reconstruction of Hupix tiles and then tiling them into a single image. The top left image here shows the temperature at 2 meters after reconstruction in Hupix projection space and reprojection back to latitude-longitude coordinates. The top right image shows the difference between the reconstruction and the ground truth. And what you can see is that there are some artifacts that appear along the seam lines where 2 adjacent Hupix tiles are joined. So I highlighted them in these red ovals. And this unfortunately happens because the reconstruction of one tile is done independently from reconstruction of a neighboring tile. So some contextual information is lost. So in order to address that problem of discontinuities and stitching artifacts, we tried different techniques, but the simplest one was simply to come up with an alternative Hughes representation that essentially has an overset Hughes mesh that goes slightly beyond what Hughes has and includes edges, some borders. And so we would reconstruct, let's say, those three Hughes squares, red, green, and blue, with these additional borders. And then we, on the composite image, we would use the superimposed edges in order to blend the presentation between different Hughes images. So essentially, we would artificially smooth and blend multiple images into a single one. We also evaluated different neural architectures for lossy compression and decided that we have a prior network, which is a special type of autoencoders, optimizing the Shannon entropy, and result of the discrete code will be the best one. But the architecture had two stages with a second stage that models the variance in the latent presentations in the first stage. And this would enable us to capture spatial correlations. So how did the method go? How did it turn out? Well, we had three goals for our project. The first one was to minimize storage, to lossily compress atmospheric data with 100 times, 500 times fold reduction of storage size on disk with low median errors. And over hundreds of experiments, we investigated the ray distortion curve for different compression ratios. We focused on compression ratios of at least 100 times up to 2,000 times. And we measured that at 1,000-time compression ratio, the Haber-Prior model, which was our best model, obtained a mean absolute error of 0.4 degrees Celsius for temperature and 0.5 meter per second for wind speed. Then our second goal was to minimize the number of pixels above given maximum error thresholds. So in addition to the usual average metrics, we looked at the distribution of the error, and we observed that the Haber-Prior model at 1,000 times compression had less than 1% of the pixels with an error greater than 2 degrees Celsius, or 200 meters squared per second square for geopotential. And the last target was the most challenging one because we wanted to avoid blurry predictions, meaning errors at high frequencies. And of course, this was hard to avoid by the very nature of compression and reconstruction. So we analyzed the spectra of reconstructions. We noticed that our best 1,000 times X Haber-Prior model had smaller reconstruction errors than our baselines, but it still had persistent blurring, even if it was reduced. And but actually, a lot of that error was introduced simply by virtue of going from latitude, longitude to Hughes and back. So just the act of interpolating was already introducing blurriness. And then we looked into the predictions. We looked at specific cases. So this figure, for instance, here shows reconstructions done by the Haber-Prior model during the hurricane on 5 October 2016. The model compresses the data 1,200 times, 1,280 times. And from top to bottom, you have temperature at 150 hectopascals, humidity at 1,000 hectopascals, and wind at 1,000 hectopascals. And you have the ground truth, reconstruction, and the residual error. So the errors seem relatively small, but we, as I mentioned earlier, were concerned about the reconstruction of extreme events. So this figure here shows reconstructions of the Haber-Prior model during that hurricane and the eye of a storm of Hurricane Matthew. Luckily, that eye of a storm was still visible on the images of wind and geopotential, unlike the baseline, where that at a slightly lower compression ratio, the eye of a storm basically disappeared. We also looked at heat waves. So other kinds of extrema. So here we're looking at the 2015 Indian heat wave, and globally the mean absolute error is about half a degree Celsius. Most of the area of interest is under 1 degree error. 1 degrees of error. But the residual shows a few scattered areas near Bhutan or Karachi where reconstruction is overestimated by up to 2 or 3 degrees Celsius. So that may be a problem. This other example is showing a reconstruction anomaly. But the reconstruction anomaly is actually highlighting an artifact in the data. So we realized that the global error was very low, but there was a maximum error of 14 degrees Celsius. We tried to find out where this was coming from, and this was over Antarctica, where there was an artifact of very low temperature with some ringing artifacts, almost like a compression artifact, or here's something coming from simulation. And the reconstruction method actually smoothed over that simulation artifact. Is it a good thing? I don't know. Okay, so let me now finish the talk with the applications to climate research. So we're interested in working with CMIP6 data and climate data. And that data has multiple realizations. So it has, by nature, many generated responses. So what we did is that we trained the Haber-Prior model on one run of a variant of a climate model, and we compressed the data of all the other runs, over other simulations, with a ratio of about 180 times. And we obtained error statistics which are very similar. So in other words, we believe that we could leverage compression models to compress multiple runs of a climate model with similar error guarantees. And this would potentially be something useful for climate scientists. We published our early findings on arXiv, and we're currently making some improvements to the model, and we hope to release both the compressed presentations of ERA5 and of CMIP6, the climate data, as well as the code base for researchers to be able to build upon. And on this, I'm going to close my talk, and thank you very much. And I'm looking forward to your questions. I may have to leave the room, but I can take them by email.
Truly brilliant talk, Piotr. Can you hear me on this microphone?
Yes.
Yes. Okay. So any question from the audience? There.
Yes, thank you for the very interesting talk. Actually, two questions, if we have the time, I don't know.
Yes.
So the first one about the medium-range weather forecasting. GraphCast was trained on ERA5 data and then also validated or evaluated against ERA5 and compared then with the HIRIS. Have you also compared it or evaluated it against observation data, station data?
Yes, I believe, but it's yes, and this is actually the ground truth realization. That's what happened with the hurricanes, I think. Okay, so now it's very interesting. You see the usual process of someone walking and getting kicked out of a room. Yes, so it was compared to ground truth data, but these data, of course, still need to be represented as global dense grid. So there is a process of data assimilation that needs to happen. But the one best example of verification comes from hurricane prediction.
Mm-hmm. Okay, and does it also it's better than the HIRIS when comparing to observation data?
I would recommend you to check on the latest work.
Okay.
I haven't been working on this myself, but I think it becomes useful. Yes.
Okay. Yeah, thank you. And maybe if you have the time for one more question, or?
Yes, please.
Okay. Yes, the AI models, as you also said, tend to blur and to underestimate some extremes, and that's maybe because this underestimation of extremes, this blurring, leads to smaller RMSE. Is it right? And do you have some measures to improve this?
That You mean that the errors, or are you talking about compression or prediction?
Prediction.
Um, yes. So if I understand your question, sorry, can you ask it again?
So these AI weather models tend to blur things out. For example, cold front is blurred, right? And also extremes are not that extreme as they are in reality, because this leads to a smaller RMSE if you don't forecast, if the model doesn't forecast these very extreme, so it underestimates the extremes, right?
Yes.
And
yes, so the way to deal with this is to use more generative models. So in nowcasting, we used GANs. And in the case of medium range weather forecasting, they used GenCast, which was actually based on the diffusion model on top of the graphical neural network, in order to be able to model better the extreme events. Yes, but by definition, the RMSC tends to favor blurry predictions. But
exactly.
essentially, you need to be very careful when you optimize only for that loss function.
Okay, thank you.
Thank you very much. It was a pleasure and a delight.
And I think one thing that Piotr maybe didn't mention, but was just the computational efficiency is radically different, right? Like the GraphCast using a single TPU predicts like in under 1 minute compared to the numerical simulations, which is like, I don't know, hours on a supercomputer.
Exactly. So there is a very nice, I think, synergy that happens between the numerical prediction models and those deep learning models or generative models. We need absolutely the numerical prediction models, even just to provide assimilation data, but at the same time, and to provide grounding. But the deep learning models are essentially what allow to make multiple realizations under different conditions. And so to essentially explore the space of possibilities and to understand the impact of different variables.
Excellent. I don't
So
know
this
if
is where they work well together.
I don't know if you still have quiet space there for another question.
I have to run.
Okay. So then, thank you, Piotr. We will share your email if the audience has more questions, then they will reach out to you directly. And thank you so much. Another round of applause to Piotr.
Thank you very much.
He really was kicked out of the meeting room.